So let's get to the lecture, and hopefully this one will be quicker today. It's It's going over noise in more detail. So yesterday we talked about different sources of noise and how we quantitatively describe those sources of noise, but also we can describe noise based on this description of color, which has to do what their frequency response is, how that behavior is mathematically. We've been working with white noise so far, but there's also other colors of noise. Again, these asterisks are just emphasizing what you might need to know for quizzes in the future. Plotting the spectral power density. So making plots of the frequency responsive noise based on the color or the source of the noise. And then Noah's question yesterday kind of led into this point of how you determine what type of noise is present and how you can reduce that type of noise when he was talking about environmental noise. But we'll talk about all four: the thermal, the shot, environmental, and flicker noise, in ways that you can reduce that. Okay. I guess maybe I should keep that open. And then some important things for next week. You can, when we're talking about signal to noise ratio, an important way to characterize your instruments is a dynamic range. So what frequencies or what signals can it pick up or and work? And that will relate to the lock-in amplifier, which will be Lab 5, where the dynamic range is an important parameter with that. So we'll go have a whole lecture in lock-in amplifier next week, but also next week we have a quiz. So I just want to go over it briefly. So getting into the colors of noise, this just means what is the power spectrum of the noise in the relation to the frequency. And the reason we describe it with a color is just an analogy to light. So that's where the color aspect comes from. That when we talked about white noise that you guys have been working with, we talked about that. It's called white because it has all frequencies in the same way that white light has all of the colors of the electromagnetic, of the visible spectrum present in it. So if we want to quantitatively describe how this scales with frequency, we would say, since it's a flat line, this would be the frequency raised to the 0 power. It would give you a constant value or a flat line there. So with all the other colors, this would have non-uniform density with the frequency. So you're going to have...
would you be able to say that again? I think the sound issue is happening.
Yeah, sorry. Is it sounding okay right now?
Mm-hmm.
Okay. So I was saying that with white noise, it's just like with white light, where it has all those frequencies present in white light. And if we want to quantitatively describe it, I wrote this as the frequency raised to the 0th power. So something raised to the 0 power, that will give you a constant. So in the same way, when you guys were measuring what the Fourier transform of white noise was and you got a flat line, that's what this f to the 0 represents. Does that clear it up? What was missed? Okay. So then any of the other colors are not going to have all frequencies represented. So again, in this analogy to the electromagnetic spectrum, we can talk about lower frequency noises. So what color of light is at lower frequencies? What end of the spectrum? Anybody? Did the sound cut out?
Red.
Yeah, so red. So if we want to qualitatively talk about noises that have more contributions from lower frequencies, this would then be the red end. So this is if we're using qualitative descriptions, you can just say redder noises. But there are quantitative descriptions of different colors of lower frequency noises. So one of those is pink noise, and you can think about pink being between a mixture of red and white. So pink noise has lower frequency, it's at the redder end of the spectrum, and it scales quantitatively with 1 over F. So with the scaling of 1 over F, we'll do a plot of this. What this means is that you're going to have a decrease of 3 decibels in the noise per octave, and each octave has the same amount of energy. So if you took a range of frequencies 40 to 60 hertz and 4,000 to 6,000 hertz, those would all have the same power within that band of frequencies. So pink noise is 1 over F. I'm saying it's between red and white because quantitatively, if you talk about red noise, it scales even more drastically with the frequency. So this is 1 over F squared. So that's why if you're trying to think of does red decay faster or pink decay faster, the red is more extreme. Pink is in between, a mixture of red and white. You'll also hear this 1 over F squared dependence sometimes will be referred to as brown noise as well. And that's because brown noise is present in Brownian motion, which has nothing to do with the color. Brownian motion is named after Robert Brown, the scientist who described like pollen particles diffusing around. So that color is just a convenient coincidence there again. So that's at the lower, when lower frequency noise is present. With higher frequency noises, this would be the opposite end of the electromagnetic spectrum. That's why we call blue. So this would scale with linearly with F with the frequency. So you have higher frequency. As you move to higher frequency components, you're going to have more contributions from those. So just like pink noise, you would have that linear dependence present there. So there's also other colors of noise that you may encounter, but you won't see them in electronics. So gray noise, black noise, violet noise. So violet noise would be F squared. And also I think an interesting way to understand the differences between these noise on YouTube, if you go and look up recordings of different noises, it's interesting to hear the difference between white noise, pink noise, blue, all of this, and how the human ear senses those different frequencies. So I mean, lots of times if you're trying to have some background noise or to help you sleep or study in the background, lots of things are called white noise machines, but I think in actuality, they're more pink noise because having those lower frequency components is actually like more of a soothing sound that when they test like the sensitivity of the human ear. But that's just an interesting aside. So with these different colors, you can also make plots of this behavior. So if we have our axes here, we can label our y-axis with our power spectrum, and this is going to be in units of decibels. So this is going to be a log scale on the y-axis. And then on the X scale will be our frequency, which will also be a log scale. And I have those little tick marks to emphasize that. So if we plot our white noise source, you guys already made plots of this in a lab, you would just have a flat line here. So this is F raised to the 0. Then walking through the different noise sources or the different colors of noise that we talked about, if we have pink noise, this would then be on a log scale, linear decline in that frequency. And then with red noise, it would be even more drastic with that 1 over F squared. And then for the opposite with blue, it would just be flipped over where that white line is, and it would be increasing here. So this would be a noise spectrum plot based on the color. So do you guys have any questions about the different colors of noise right now?
So you mentioned something like the pink noise decays like 3 decibels over, like, do we need to know that on this graph?
So with this, yeah. Sorry, the sound was cutting out. So your question was about the 3 decibel decay per octave?
Yeah, yeah, per octave, yeah.
Yeah, so if with this plot, if we put labels on the y-axis, then we could emphasize that. So I can redraw this and include that, and I'll upload that on Canvas. So if we want to include that, that 3 decibel decay, I'll include a figure with that. So we could be even more quantitative with this. Any other questions right now? Okay. So we can also make these noise spectrum plot based on the source of the noise. So just yesterday we talked about these different sources of noise. So I'll ask you guys what color each of these noises were. So for thermal noise, what color was that noise source, if you guys remember? Or with the equation, we had the bandwidth present in there.
It factored with the square root of the bandwidth,
Mhm.
which means it's probably red noise.
No, so think about if you change that range of B, would that change the amount of noise present?
Hey, so it's probably bluer.
So if we have the same, if you're changing the bandwidth that you're looking at, the range of
Bluer
frequencies
noise.
you're looking at,
Probably
would
red,
that,
right? Red and brown.
so if you change that range of the bandwidth there, you would still have the same amount of noise present. If you're looking at as long as that bandwidth is the same range. So if you have delta B, that will be this, you'll have the same amount of noise. So that means that thermal noise is white noise present there. So
The bandwidth
also,
is not a function of what range you're looking over, but instead
sorry, can you repeat?
so bandwidth is just a function of the actual value of the range, not what the range is measuring over.
Yeah, so what range of frequencies are you collecting your data over?
But it doesn't matter the values in which you're measuring over.
Yeah, so it just matters what the most positive value to the most negative value that you're,
Then it's white noise.
yeah, so that would be white. Yeah. So similarly, the shot noise has that square root of B that's present in there. So that one is also a white noise source. So for flicker noise, we also called this yesterday.
Pink.
Sorry, was it?
Pink.
Yeah, flicker noise, pink, obviously because it's 1 over F. That's what this same equation we wrote for pink noise. And then finally, environmental noise. There's no color associated with that one because it's just at very discrete bands that are present there. So we can draw all of these noise sources on a plot. So just like on the last plot, we just drew based on color. Let's draw it based on source now. So it's important to know what color each of these noises are and also what frequency they're at. So we can have our axes again, where we can show with thermal or shot noise that this would be a flat line. So the same as the white noise we drew on the last slide. With the flicker noise, do you guys remember which frequency range that flicker noise was prevalent?
Under 100 hertz.
Yeah, so under 100 hertz, so we would just draw this with the 1 over F behavior, but only prevalent at under 100 hertz. And then with the environmental noise, we would have these peaks that would be present at, let's say, at the 60 hertz signal, at the AM signal, the FM signals. I even drew like a little peak over there that, like, let's say you were doing a measurement when classes were changing and you had vibrations in the floor, that would be very low frequency, that you could draw those different types of peaks. So I guess an error that I probably should have drawn, let's see if my pen will work, the flicker noise more like this. Because after 100 hertz, it has such a low contribution that you don't see it. So Let's actually draw it that way. So this would be each individual noise plotted on this frequency plot, but then what we can do is add these noise sources together. So if you were doing a measurement over this entire frequency range from like 0 hertz to the megahertz range, you can then add all these contributions together. So let's say we have like, you can also say there's a line for shot noise as well. So you would add all these noise contributions together and get a total noise plot. So you can see like this flat contribution would be the thermal plus the shot noise. We have the flicker noise at below 100 hertz, and then you have your environmental noise shown as those peaks. So any questions here with drawing plots of your noise spectrum at all? So this was very related to the end of lab 4, where you guys were looking at different ranges here. Okay, cool. So we can move on. So this is getting at Noah's points yesterday of reducing noises and also distinguishing. If you're doing a measurement, you find that your signal is quite noisy, which type of noise is contributing to your measurement? How can you distinguish what you should be trying to reduce? And the way to do this is if you take a look at the equations. If we start with thermal noise, let's walk through each of these variables where we can take a look. If it's thermal noise, something we can't change is 4 or the Boltzmann constant. So any constants that are in your equations for noise, you can't really isolate. Those are going to be the same no matter what. But we can walk through each of these variables. So one thing is if you increase the temperature of your source resistance that is having these electrons being thermally produced, can you increase the temperature or cool it down and see if your noise scales with the square root of T? So this is square root of T. So this is one option, but it's not always practical with certain equipment that you can't just like stick it in a vat of liquid nitrogen or heat it up. It could damage different components. So that might not be an easy way to isolate that. So another thing is, can you vary the source resistance and see if that scales as it's expected? And then the last thing, if we're walking through this equation, is the bandwidth, but it's oftentimes difficult to vary the bandwidth. You're typically interested in signals at a certain frequency, so changing that bandwidth can be a challenge. And then also, shot noise scales with the square root of B as well, so that wouldn't tell you if your source was thermal or shot noise. So those are ways that you would identify that you have thermal noise present. And then if it is a problem, you can then reduce that noise. If you're working in the range of nanovolt signals, this is when you're working with oftentimes trying to reduce that noise. So one thing that you'll see in many labs is working at cryogenic temperatures. So this is in like Professor Rule's lab or Professor Gao's lab. They're working with like liquid helium to cool things down very close to, I think they're at like millikelvin or so. Or also people work with liquid nitrogen to reduce thermal noise. And again, identifying reducing noise, similar, walk through the equations. If you can, lower the impedance of your source, and you can use filters to decrease that bandwidth if you know exactly what band of frequencies you're looking for. You can use your bandpass filters, low pass filters, and the like. So we can do very similar things with shot noise. Again, let's take a look at this equation. 2 and the fundamental charge of an electron we can't do much about, but the main thing that we can change here is our signal strength. That's average current that we're looking at. Do you see noise increase with the square root of your current as you increase it or decrease it? And again, the bandwidth won't help you determine between thermal noise or shot noise, since you can see in the equation we have the same square root of the dependence. So shot noise, I guess, is more limiting. It just has to do with your average signal that you're looking at, the strength, and that's the way that you'll try to reduce it in your measurement as well. So shot noise becomes important when you're looking at picoamp to femtoamps, and you'll even see this show up with the KDMM, that it can't even detect down to picoamps or femtoamps because of the shot noise with the equipment that we have. So one thing is like, can you decrease your signal strength? That's what you would look at with the shot noise equation. At a last resort, you could decrease your bandwidth, but the main way that people overcome shot noise is more the software approach of ensemble averaging that we talked about 2 lectures ago. So as you collect more and more data, those statistical variations will average out with the square root of n that we went over. And then with our last 2 noise sources, we talked about flicker noise yesterday, that there's not a really well-described source, so it's not always easy to remove. But there are different flicker noise or pink noise behavior with flicker noise with different electronics. So in the lab, we're using like carbon resistors, and these have carbon grains in them. So let's say like we're looking at like, let's say this is like 100 nanometers or so. There's carbon grains in these carbon resistors. And it's been figured out that flicker noise arises based on the boundaries between these grains. So this will lead to flicker noise that's around 0.1 to 3 microvolts per decade of frequency. But if instead you use the fancier carbon film resistors, there might only be 1 grain or 1 boundary at that length scale. So there's a lot less flicker noise there. The problem is these carbon film resistors are more expensive. That's why we're not using them. But if you're trying to do low frequency measurements with some sensitive instrumentation, it might be worth buying these higher priced electronic components compared to what we're using in the lab. And also, because flicker noise is only prevalent below 100 hertz, if you have a way to modulate your signal so you can measure it at higher frequencies, you can overcome frequency or flicker noise as well.
Professor.
Yeah.
So when you say that flicker noise like scales with 1 over f, do you mean like 1 over the frequency of the AC signal that you're sending through your resistor?
Yes.
Okay.
Yeah. When it's below 100 hertz. In terms of electronics, but with other measurements, you might see flicker noise show up at higher frequencies too. Okay. Then the last noise is then the environmental noise, which Noah pointed out yesterday. You can do some electronic shielding. And I guess pointing out to the people in 208 and the physics engineering students, if you're designing something, this is where some engineering concepts come into play. If you know you're going to have to remove some environmental noise, think about it early in your design of what you can shield at a certain point. Maybe in our lab space, if we're using the RAL board, if you put like a metal box connected to ground around your circuit, if you're doing some long measurement, that might be fine. But let's say you're sending something, building a device that's going to be sent up to like the International Space Station. Space is limited. So thinking about where shielding should go in that device design should be thought of earlier than later, because it's not always easy to incorporate that. Or if you're working like with commercial instrumentation, like these black boxes, it might not always be easy to open it up and introduce a shield where you need it. So that's an important thing with trying to reduce environmental noise. So any questions with figuring out what noise sources you have or reducing it? Okay.
Oh, can I ask a question?
Mm-hmm. Yeah.
So I think when we talk about thermal noise, you said signal averaging won't help us.
Mm-hmm.
But why does it help with the shot noise? Because I feel like the functional form is very similar between the two. So why does signal averaging work for shot noise but not thermal noise?
Yeah, so Shot noise, if you're collecting data over time, the statistical variation that's taking place is taking place over time when you're doing shot noise. You either detect an electron at this point or you don't, versus time. So that Poisson process will be averaged out since it's over time. With thermal noise, what's happening is you have a buildup of electrons. So if you're only building, there's not a time dependent process taking place there. It's just only going to be more and more electrons that are being produced in your resistor with the thermal noise. So if you do ensemble averaging with thermal noise, it's just going to keep increasing, but the time dependence of the shot noise lets you average it out.
Okay, thank you.
Okay. And yes, also this last bullet point here is just mentioning that there's also all the other noise reduction methods that we've discussed that you can also incorporate to try to reduce some of these noise sources if you use them properly. Like yesterday, we were talking about correlation, that if you correlate your signal, noise has very low correlation with itself. So it can help reduce that as well. We talked about that match filtering. Okay. So one last thing about signal to noise ratio is a way to quantify your instrumentation of what signal ranges it works over is called the dynamic range. And this will, when you're looking through the manuals of the equipment that you guys were using, you can also take those values of what's the lowest frequency that it can measure versus the highest frequency, and taking a ratio on a log scale will tell you that's another way to characterize your instrument. So the maximum is related to what's the max signal that your instrument can handle, the max voltage, max frequency that it can detect, but the minimum is associated with the noise. The equation that we have here for the dynamic range is going to be like log base 20. So it would be in the decibel scale of your maximum signal over your minimum signal that you can detect. So I just want to bring up that this is another way to quantify the performance of your instrument and is related to the noise with that minimum value there. So with this dynamic range and the lock-in amplifier that we'll be talking about next week, it's important to know that based on the settings of this lock-in amplifier, the dynamic range changes, and you can overload your instrument very easily with, I guess, this max setting. So that's why I'm bringing it up now, since it's kind of a transition between the two. Because just as a brief introduction to the lock-in amplifier, this is what we'll be going over next lecture, the next lab. And we're using acronyms or abbreviations for all the equipment in this lab. So it'll be abbreviated LIA. And it's a piece of equipment that lets you detect signals that have very low signal to noise ratios, much lower than what you've been able to detect in lab thus far. So I think most of you guys in lab 3, when you were varying the signal to noise ratio, you guys were able to say, oh, in the frequency domain, I think most people were able to detect like a single peak in the frequency domain for your square wave of about 0.3 for your signal to noise ratio. In contrast, the lock-in amplifier is able to detect signal to noise ratios 2 orders of magnitude better than that. So we would say roughly around 0.01. So this is an improvement by a factor of, I guess sometimes can be upwards of 1,000 or 10 to the third. So the way that the lock-in amplifier works, I'm just going to talk conceptually about it very briefly, but we'll go into lots of detail next week. And I have up in this upper right-hand corner, just the front of the lock-in amplifier that we would be using in lab, but hopefully we'll go over some videos or some demos with that. But you can see that there's a channel 1 input over here. This is a channel 2 input right next to it. And those 2 channels are your signal. You feed in your signal, but you also feed in a reference signal as well. And you take those signals and you multiply them together. So the reference signal is typically provided by the lock-in amplifier itself at a certain frequency. And you mix these signals together. So the first thing you do is you multiply them. Then you integrate those signals together with a low-pass filter. If you guys remember from Lab 3, the low-pass filter will integrate. And when these two signals are at the same frequency, this integral will not equal 0. Everywhere else, it will equal 0. So once you're locked into that frequency, you can actually see a value of, I guess, this the mathematics that we're doing within the lock-in amplifier with these two signals. So once those are, you get a value that's not 0, you know that's the frequency of your signal. So a way to describe a lock-in amplifier is it's a arbitrarily narrow bandpass filter that it's right at the same frequency that you'll see your signal and your reference voltages locked into each other. So that's why it's called a locked-in amplifier, that you'll actually see a signal taking place there. So it has very high sensitivity in nanovolts. So this is where the dynamic range aspect comes in here, that I'll probably bring this up many times since you guys won't actually be using this lock-in amplifier in lab, that when you move up to junior lab or senior lab and you have to use a lock-in amplifier, be very careful not to like overload the lock-in amplifier, because we don't need to damage these. So next week we'll be talking about, I guess, the actual components of the lock-in amplifier that will do the multiplication or the integration and what your output would look like. But this is just a brief introduction of what it is, and we'll go in more detail next week. So I think that's most of what I had for today. Does anyone have any questions?
Could you just go back to the previous slide, please?
Yeah.
Can you give me an example of what a reference signal would be in like an actual lab setting when you're using a lock-in amplifier?
Yeah, so these lock-in amplifiers actually have a built-in reference signal. So it would be like a sine wave that you can select. Do you want a kilohertz sine wave, a megahertz sine wave, hertz? I'll have to go back and look at the details of like which ranges those are at. But you actually have that built-in reference, and it's typically you extract it, I guess, from the back of the lock-in amplifier, and you have a coax cable coming from the back and connecting to the front. But I guess if you need something that is more unique than what is built into this lock-in amplifier, you can also provide something from like a function generator. Everyone good with the slides? Do people need this up longer? Okay, I'm gonna stop recording.